Alex Schmidt from the Biostats program at McGill University. I'm helping Peter managing the chat. If you have questions during the session, feel free to write them on chat, or if it's a quick question, you can unmute yourself and ask, right, Peter?
Please, yeah.
So whenever you're ready.
Ready to go? Well then, thank you for coming back for the second session. Plan today is to talk about regression. Like yesterday, we talked about density estimation. Today about regression. And you can already see here in the title slide. Those are like two examples of regression. I think it's a little bit out of focus, at least maybe it's just my screen, yeah. But the main thing to see here is in the left slide, you're seeing survival functions. So for survival analysis for event times, it's customary to show distributions as survival function, which is just 1 minus the CDF. So for all intents and purposes, just simply take the complement to 1 and you see the CDF. The important thing is that you see here something like 8 different distributions. And each distribution we could label something like, so each of them is like a G sub X, where the X is any one of these 8 combinations down there. Those are 8 combinations of baseline covariates for cancer patients. And it's time, I think it's time to progression. It's probably, it might be overall survival. And you can see how there's different distributions these patients. That's what the whole story will be about. And rather than using parametric models, we'll use BMP priors for these unknown distributions. And in the right panel, you just see like a little twist to that. If there's a binary covariate, like in this case, it is like 2 different types of like normal pregnancies and abnormal pregnancies for Chilean women. We can then use it for classification. We'll come to that towards the end of today. So plan for today is to talk about the use of BMP for regression. And talking about regression in BMP, it is convenient to think about regression as a family of different distributions in the following sense. So I'll just make this statement here. I'll make this statement. I'll make a picture for this statement. For the purpose of the upcoming discussion, it's convenient to think about regression as a family of probability measures. Consider the following situation. Here we have a covariate. Say there's like 3 different levels for that covariate. For example, these could be like the 8 different combinations of covariates of the women on the title slide. Here's the outcome, for example, overall survival. And for each value of X, we have like a different distribution of the outcome. Maybe for, say, this is X equals 0, 1, 2. Could of course be continuous. It's just easier to make the picture for a few discrete values. For X equals 0, say the distribution might be something like this. For X equal 1, we see maybe a slightly different distribution. We see like the blue distribution, which might have slightly shifted down there. And then for X equal 2, we might see the orange distribution, which might then be like this. Can you see how the distribution of the outcome changes as the X changes? And I try to make that such that, overall, kind of if you try to track the mean, it kind of goes down. So you could think of regression as just a family, a sequence of random probability distributions. Here's G0 for the distribution on the covariate X equals 0. Here's G1 for the distribution under the covariate equal 1. And here's G2 for patients under covariate equal 2. That's kind of a very general way of thinking about regression. Obviously, the X would typically be much higher dimensional. Just here I tried to draw it, so I made it 1-dimensional. and all kinds of simplifications are possible. In the extreme case, so there's now 3 different levels at which we can play that game. In the extreme case, we could assume, let me still go back to the picture here. We could assume that that each of these distributions, they all look the same, and they're just shifted. Let's do that in red. So in red, I'll do here the first variation. If for each covariate level we have the same distribution, and we just shifted same distribution down a little bit, then we are in the first case. So this one is the first case where we have the same distribution for each case, and we are just having a location parameter that moves with that function f sub theta of x. And then we might want to go like non-parametric just on the residual distribution. So maybe just this red residual distribution G, we go non-parametric on it, and it need not be a normal, and it could be something different. And that is being done quite a bit. So many times when you read about non-parametric regression, not Bayesian non-parametric regression, that might actually refer to that case, that the mean function is a parametric function of the covariate, for example, just a linear function, and then we are non-parametric on the residual distribution. Alternatively, it could be, let's make that here the green case. We could just go, and I'll maybe make a new picture for that. We may just go non-parametric on the mean function. So the mean function could be something weird, and we go non-parametric on this one. So let's call that f, and we have a non-parametric prior on that mean function. But maybe the residual distribution, we might just assume just a vanilla normal distribution, so just Gaussian kernels around the mean function, and that would be the green case too. That's also being done. Then you would need a prior for the green guy. You would need a prior for that regression mean function. We didn't talk about that. Yesterday we only talked about BMP priors for unknown distributions, but there's a whole literature also for BMP priors on unknown mean functions. They are also infinite dimensional creatures, and we can put probability models on them. What we really want to talk about today is the third one. It's like the fully non-parametric case, which is what I started out with the picture on the right side, when we have the black, the blue, and the orange distribution, and we really need then a prior probability model for a family of random probability measures indexed by X. So that's really the most general case, and that's what we'll talk about today. So it boils down to we need a probability model, we need a prior distribution, not only for one unknown distribution. That's what we had yesterday. For one unknown distribution, we had a Dirichlet process, or we had a Polier tree, or we had a normalized random measure. Instead of that, we need now a prior probability model for a family of random distributions indexed with covariance X. So it's become a little bit more complicated, but we'll see it's not going to be all that difficult. Before we go into a construction, the construction will actually be surprisingly simple. Before we go into a construction, maybe one more example. So here's an example. It's actually that example from the title slide only. The outcome YI, in this case, the YI is overall survival for some 700 patients in a breast cancer study. Covariates include in particular 3 different covariates, dose, whether these patients are expressing a certain estrogen receptor, and tumor size, and the derived covariate, which is like an interaction of 2 of the other covariates. So we have now covariate vector X. That covariate vector is an index for high dose, sorry, an indicator for high dose, an indicator for estrogen receptor, tumor size that's continuous, and high dose times estrogen receptor. So it's like a 4-dimensional covariate, although 2 of them are just 2 of them are actually just binary. Yeah, and for each combination, as we saw it on the title slide, for each combination, we want to see f sub x. We want to see a distribution of overall survival times. Carrying out non-parametric regression in this case will require we put a prior probability model on f sub x, where x can be any combination of these four covariates that we have there. And in a moment, I'll talk you through a very cheap trick of achieving that. Yeah. But so what we need is we need for each possible combination, and here in the next slide you can see there's here's like I think it's 8. It's something like 8 combinations of x's, and there's many more because one of the covariates, the tumor size, is actually continuous. It's not only there's only for 8 we plotted it. For these 8 combinations, we plotted this. Sorry, I always use G sub x, but I notice here we use notation f sub x. Obviously, it doesn't matter. So you see here, for example, you see the thick black one, that is f sub x for x equals 0, 0, 0, 0, all zeros. Tumor size is centered. So this is f sub x for x equal all zeros. And the other 7 lines, those show you the survival functions, means 1 minus CDF for the other 7 combinations. In order to come up with such inference, we need a Bayesian inference model. A Bayesian inference model requires a likelihood, a sampling model that's here. So this is the sampling model, or defines the likelihood function. And we need a prior probability model. That prior probability model, that will be the BMP prior on that family of random probability measures. On these, for our picture here, I just need 8 of them, but in principle, there's many more of them. What you should expect now is I have to talk you through some construction. of this prior that we need for our family of random probability measures. And it's going to become embarrassingly simple. It's going to become really simple. I'm wondering, what should I do? I'll first show you quickly the thing, and then I'll draw a picture, yeah? So this is the so-called dependent Dirichlet process, which has become very popular over the last 15 years or so. People have built entire careers on it. It's a funny one though, so it's very popular, it's heavily used, but the original paper has never really been published. So what I always reference here is Steve McEacher 1999 proceedings paper. It has never been published in a journal. But that said, it's like many papers build on it. It's a whole literature. So here's the idea. What we shall do is, what you should expect now is a construction. We need a prior probability model for a random, for a family of random distributions. Now it's again G. Sorry to switch around the notation, doesn't matter, of course, yeah. So we need a prior probability model for a family of G sub x. And we want to do it, now additionally, we want to do it in such a way that marginally each of the G sub x should be a Dirichlet process. So what we want now is, we want a prior probability model for these distributions indexed by covariates in such a way that for a particular covariate combination, the prior should just reduce to a Dirichlet process. Let's think here about three different covariate combinations. Let's first stare at the first one. For x equal x1, that means we want our random probability measure. We want our random probability measure to follow a Dirichlet process. Remember the stick-breaking definition of the Dirichlet process. The stick-breaking definition of a Dirichlet process was we can always write a Dirichlet process random measure as a summation of infinitely many atoms because it's discrete, where each of the atoms has a probability mass p sub h at a location m sub h. And the only thing that we have to change now, since this is G sub x, let's add a second index here to allow for different locations for the different axes. And all what I did now, I took this representation and I spelled it out down there, like I expanded the sum. And remember, the stick breaking definition was that the locations for the point masses have to be IID from the base measure, and the weights, they were generated by the stick breaking process. You start with a stick of length 1, and then you break off iteratively, you break off better distributed fractions of the remaining stick. That's exactly what we do for G sub x1. So at this moment, we have marginally for G sub x1, we have simply generated a Dirichlet process prior. And then we continue, and we do exactly the same thing for x equal x2. And again, those locations, they have to be independent. So we need independence across the line here, yeah? Because by the stick breaking construction, the locations of the point masses have to be independent. Same thing for x3. And again, the locations have to be independent in the line. But, and that is exactly where we get our desired model. But there's no restriction about independence in the column, or in other words, all the green point masses, we can actually make them dependent. There's nothing stops us from making the green guys dependent, making the blue guys dependent, and making the red guys dependent. And that's actually already it, yeah? So all what we are going to do is, while they are independent in a row to satisfy the stick breaking construction, we'll introduce dependence in the columns. Means we make the locations of the atoms dependent across different axes. So all the green guys become dependent, all the blue guys become dependent, all the red ones, etc. That's the idea. It's actually quite simple, yeah? I'll tell exactly the same idea again, but now with a picture. So exactly the same story again, but now in a picture. Say here is x1, x2, x3. And let's first start with the random probability measure for x1. So here I'm going to construct now Gx1. Gx1 has to be a summation of weights at certain locations, where the locations are simply an IID sample from some base measures. So let's just pick some locations here. I generate them now by hand. Those are the locations, those are the atoms. So this one here was M sub x1, M sub x2, M sub x3, and so on. And then for each location, then we use the stick breaking to construct the actual probability masses for each location. Here's the first one, here's the second one, the third one, the fourth one, and so on. That's the construction for the first one. So for the first one, I simply constructed a Dirichlet process random measure using stick breaking. And now comes the construction for the second one. For the second one, for x2, what I'll do, so the Gx2 is again a summation of weighted atoms at locations M, x2, h, and this one here was x1. What I'll do is I need those blue locations, they have to be independent, but I'll simply generate them by, so here is an M x2, 2, and this one was x1, 1. Here's an M x2, sorry, this is mx2, 2, this one was mx2, 1. Maybe here comes the mx2, 3, and so on. Can you see the idea? What we simply do is we make the point masses dependent across the axis, but independent across the atoms. And then we actually, did you notice, we cheat a little bit. We use actually literally the same. We actually use literally the same weights. So using literally the same weights, I just copy them over. And this is now the random probability measure for x2. And for x3, again, I'll do exactly the same. I'm going to get a different color. For x3, let's do it in red now. Again, I generate like the first probability mass, the second one, the third one, the fourth one, and so on. And again, they're just connected to they're just generated dependent from the earlier ones. And that way I get in here another random probability measure. And I could keep on going like this. It's not beautiful because it's discrete distributions, right? So here's then the GX3. And the important thing is that we make them dependent. We make them dependent across. Make them dependent across the covariates, but maintaining independence across the atoms, right? I have now, like in the end, what I have is I have a distribution. I have here the GX1. This is the GX1. I have here the GX2. And I have here the GX3. Each of them exactly satisfies the stick breaking construction, and they only sneak in the dependence by making them dependent across X, which does not impact the stick breaking construction at all. So that was the little trick. Embarrassingly simple in my mind, but also incredibly powerful. That's it. That's all that's to be said, actually. Yeah. So those few lines. That's the definition of the G.E.P. But there's all kinds of variations one can play then. But in principle, that's the basic idea of the G.E.P. construction. Here's the just another quick example, just to show you how flexible that is. You see on the left side, you see for another example the data. This is the data for three different survival distributions. Data for survival data is usually shown as many of you might know Kaplan-Meier plots. Think of these as just the empirical distributions of the survival data. And then in the center you can see the Gx bar, which is just the posterior expectation of G sub x given the data. And with a little fantasy, I would say that's a reasonably good fit. Like here was the in dashed, there was like the dashed line for the dashed covariate combination. This was high dose and ER negative. With a little bit of fantasy, I would say that's not a bad fit. And here on the right side, you see the G hat using a parametric model, something known as the accelerated failure time model. You can see that the parametric model fails to capture some of the features of the data. Maybe it's not as dramatic as it seems to my biased eye, but just to demonstrate, it allows a quite flexible inference. The basic construction, I only introduced the dependence on the locations of the atoms. In general, though, you can play variations. See here we have the dependence, like the atoms have can you see that second index here? The atoms have like the X index to make them vary across covariates. What we did here was, we did the same thing on the weights. Can you see that also the weights here include now an X index? So in general, you could also vary the weights across X. It's usually not so commonly done for the simple reason it's very easy to introduce dependent prior on the locations across X. You can do anything starting from just a straight line or things like that. Making the probability masses dependent is a little bit more delicate again, because you have animals that have to add up to 1, have to be non-negative and all that. So that's why the first variation is probably the most common one. I would call it the common weight DDP. So the common weight DDP is exactly what we had on the previous slide, where we only introduced the dependence on the covariate in the locations. Alternatively, though, we could turn it around and we could have common, so sorry, in this case it was common weights. Instead, we could have common locations and only vary the weights. There's some reasons to do that. In my mind, the main reason is to avoid problems related to extrapolation. See back here in this picture. Let me just redo the picture in a different scale. It's the same old problem with extrapolation and regression. If in our data we have just values for x equal 0, 1, 2, we might end up estimating these distributions. So here we get a distribution like this. Here we get a distribution maybe like this, and maybe here it moves even further down. But if you want now prediction, for some x way out there, say x equal 10, well, if you do naive prediction, what you might end up doing, and we didn't talk about details of the computation at all, but what you might end up doing is, here were the first probability masses for the first three axes. If you do naive prediction, depending on how you make them dependent, you might send it way down here, right? Here are the probability masses for the second one, say here, here, and here. And if you naively send it down, you might get the same thing for all the others. You have simple extrapolation problems, yeah? You might then get like a really weird distribution down here that is just very unrealistic. Depends on what's your model for connecting the axes. Here what I simply did was I just connected straight lines. You can make more sophisticated things. So that's one motivation, to have common locations, not to move on the locations, and to just allow varying weights. That's the second case. The third case is a bit weird. Common both, but we scramble the way how we allocate weights to locations. That's a bit specialized. The first two are about the most common ones. And I want to talk in a little bit more detail through a special implementation of the DDP, known as the ANOVA DDP, also the linear DDP, SL DDP. At which moment will now become specific. So what's going to happen now, we are going to have a specific model for the MHX. So a very specific, oops, I screwed something. Very specific assumption on how these locations change over time. Before we do this, maybe this is a good moment to stop and break for a moment. Are there any questions, any comments? Any general comments about the DDP? Like I could imagine, like in some way, maybe the construction is seems too simple, and you might expect something more fancy and complicated than what there is.
Peter, there is a question in the chat. In real data application, in real data application, is it common to generate the distribution according to all covariates, 100 or 500, for example?
Good question. Pointed answer, yes. Longer answer. Of course, in the end, we're only going to work with the distributions for the covariate combinations that they actually observe, which is always finitely many. But in principle, the model is specified for any covariate combinations. If those include continuous covariates, then we have like a more than countable family of random distributions. You asked, is it common to generate it for many different covariate combinations? Well, we have to consider it for all the covariate combinations that appear in the likelihood. Means we have to at least evaluate it for all the covariate combinations that appear in the data. And that could potentially be many, yes?
Mm-hmm. You didn't see it because it was sent to me.
Got it.
Only.
Now I see
now
one here.
Another one, yeah, from Shreen. she's...
Oh, very good one. How do you incorporate specific correlation structure? I think the question is probably about correlation across X, right? Like this could be, for example, to be specific, if the X, like if we are back to the motivating example there with the patients in the breast cancer study, here could be X, say high dose, blah, blah, blah. And here's X equal low dose. And let's put all the other covariates at 0, yeah, because they're all centered. Then here's the distribution for a woman treated at high dose, whatever it is. And then essentially the question is now, if here's the distribution, let's call it G sub high for a woman treated at high dose. And now we want to think about G sub low for a patient treated at low dose. The question is now, how do we specify the correlation? For example, this first guy has to correspond to a first guy here, right? It boils down to the question, how much do we think that could change? Like the question is from here to here, how do we get there, yeah? In G.E.P answer, how much the changes should depend on like your clinical judgment. Like knowing the treatment, you might have an idea of changing from high dose to low dose, how much could that potentially impact the overall survival, and use that. A bit more formal answer, a popular assumption for the prior on the M sub XH, a popular assumption for the prior on the M sub XH is a Gaussian process. Many of you might know Gaussian processes. If you don't know it, a Gaussian process for a finite number of x's is simply a multivariate normal. So a common assumption is just a bivariate normal with some correlation. And talking about that correlation, in the end, you have to elicit it and think about the problem. So that's almost like throwing a question back on you. It's just being honest, yeah. Like you have to think a little bit about how much the distribution could change over different x values.
There is another question.
What about continuous covariates? Yeah, a Gaussian process could very well be indexed by continuous x. That's not a problem, yeah? Mm-hmm. So this could be a continuous, for high and low dose. Dose need not be only high and low. Depending on what of the treatment, you might be able to consider any dose in between, right? Then if you assume a Gaussian process on the MXH as a function, like indexed by x, then that includes the continuous covariate x potentially, yeah? And we'll come up, now in a moment, we'll talk about another even simpler solution, yeah? So Gaussian process is a typical one, is kind of the generic one. In a moment, we'll talk about an even simpler one. Thank you, all good questions, yeah, good comments. Like as it's already reflected in the comments, the problem of specifying a DDP prior essentially boils down to coming up with a good prior probability model for the MHX as the X varies in the covariate space. This is really what it all boils down to, right? Like all your questions were focused on that, I think brilliantly so, because it's really cutting to the core of the problem, yeah? And here's perhaps one of the easiest ways of doing that, which is the linear DDP or ANOVA DDP. It's a DDP prior for when the X is just like a categorical X, like it was almost in our motivating example. So for example, this could be X equal indicator for high dose, indicator for ER positive, etc. So it could just be categorical covariates. If it's just categorical covariates, what's your favorite probability model? What's your favorite probability model to induce dependence across categorical covariates? How about just vanilla ANOVA? What you see down there is, so let's assume we have two covariates. Let's assume we have two covariates. Let's call them U and, sorry, let's call them V and W. And maybe the V can be 0, 1 and the W can be 0, 1. If you write down an ANOVA model for two factors, dose and ER, then you might parameterize an ANOVA for dose and ER. You might parameterize it as overall mean plus a main effect for dose plus a main effect for ER. And that could be a basic parameterization of an ANOVA. And that's exactly what we do. Just we have to do it for each of the point masses. That's why there's that second index H. There's that additional sub-index H. And then just put an ANOVA prior on the ANOVA effects. That's it. Doing this is a very cheap way of making the, remember that the MXH, those are the locations of the atoms for our discrete probability measures. An easy way to make them dependent across the covariate levels, if the covariates are categorical, is just assume an ANOVA model, just write down an ANOVA model. I would like to elaborate on that a little bit. What I'll do now on the right side on the whiteboard, I'll spell out the ANOVA DDP in terms of the discrete probability measure. Let's look again in a bit more detail at the ANOVA DDP. We have G sub X is equal, I'm hesitating for a moment whether I should already introduce a continuous kernel. See, what's going to come up in a moment is I'm going to say that these discrete distributions are really ugly. For many applications, we need continuous distributions. How do we achieve continuous distributions? Well, just take each of these point masses and smear it out. And that means an additional convolution with a kernel, for example, a Gaussian kernel. And then we get a ANOVA DDP mixture of normals. Let's make that then maybe already like this. So it's summation of normal kernels. I add an additional normal kernel. This is G sub X of Y, where Y could be the overall survival of a particular patient. A normal kernel centered at, here we have the M sub X and fixed kernel variance. And then we have the F sub X of M sub X. This is just moving from the discrete probability measure to a continuous probability measure by convolution with the additional normal kernel. Where that M sub X we could write as mu plus alpha sub V plus beta sub W. And if we replace, like, the integral is just a concise way of writing a summation. And then when we write the summation of summation index H, that would introduce the second index H there. So this would be the DDP ANOVA model with an additional convolution with a continuous Gaussian kernel in this case. There's one thing I want to point out. We could alternatively, we could write it, and we are used to that from ANOVA, right? We could alternatively write that M sub X, instead of saying you have to write it like with the ANOVA parameterization, I could just introduce a design vector. Let's call it, say if this one is the patient I, then this could be D sub I, could be the design vector for the ith patient. The design vector is simply a vector that selects the appropriate ANOVA effects. So DI prime times theta, where the theta could be a vector of all the ANOVA effects. So mu, alpha 1, beta 1, and whatever is needed. So for those of you who are familiar with writing ANOVA in terms of a design vector, this is probably familiar. That you can just put down a vector of all the ANOVA parameters, and introduce a design vector that picks the appropriate ANOVA parameters. The thing is now, if you write it like this, then I'm just going to copy it down, then it becomes a normal kernel centered at di prime theta sigma square, and now we can just say df of theta. The beauty is we just need to now one probability measure for the ANOVA effect. So in other words, if the dependence across X in the DDP, if that dependence takes the form of a parametric model, like a simple ANOVA model, then it really just reduces to a Dirichlet process mixture of that particular parametric model. I think this might be clear if you're familiar with writing an ANOVA model in terms of a design vector. Otherwise, maybe it was a little bit too fast. Then it just remains a footnote. If the dependence across X is a simple parametric model, then the DDP actually reduces to just a Dirichlet process mixture of that parametric model. So now we are in the position, like just one line executive summary. What we have now is we have a prior probability model for a family of random distributions indexed with a covariate. And it wasn't even that difficult. It was like a 2-line definition. And even better, computation is not much more difficult than for Dirichlet process mixtures either. We did not talk much about computation, but one of the reasons why the Dirichlet process is so popular is because computation is easy. And I would like to talk about one typical application of BMP to essentially causal inference. Like we're going to use now in the next example, we're going to use BMP, means in the particular ANOVA DDP model. We are going to use it to adjust for the lack of randomization in a clinical study, which is like a typical application of causal inference. So here's the example. Don't want to dwell too much on the details of the example. The example is about a treatment. The initial treatment is the A up here. If you remember that right now, these were leukemia patients. So there's initial treatment A, and patients are randomized to the initial treatment. But then what's really going on is all kinds of things can happen in a trial. Patients can show resistance. When they show resistance, then they get a salvage therapy. They get like a second-line therapy. The point is when those patients are assigned a second-line therapy after they showed resistance, then clinicians are reluctant to randomize. So this salvage therapy is not randomized. And similarly, the tumor could show response. This here, CR stands for complete response. But then after response, again, you could again see tumor progression. The tumor might come back. And then we need another salvage therapy. And again, that is non-randomized. Well, and in the end, all of us die. But so the problem here now is if we try to compare treatments here on the basis of the outcome, we have to be careful because that includes further down the road, that includes non-randomized treatment assignment. To compare different treatment strategies, we have to adjust for the lack of randomization. And that's exactly where the DDP will come in. We are going to use a DDP model to model overall survival for patients in this study. The way how we'll go about it is, see in that little flow chart. In the little flow chart, there's something like, I think it was 7. There's 7 different transition times. For each of these yellow transition times, we'll have a BMP prior. So for example, let's focus, for example, on this one here. When we have a BMP prior on this transition time, let me just see what notation I use. I don't remember by heart now. there is this is a transition time, let's call it F superscript 4, because it's the fourth one of those transition times if I count them from left to right. The distribution of these transition times will allow it to depend on covariates. It should certainly depend on the treatment. It might also depend on baseline covariates of the patient, etc. So we need here a prior on these random probability measures, f sub x, for x in some space, like all possible baseline covariates and all possible treatment assignments. Same way here, let's call this f super 1, the distribution of transition times from induction to resistance. And again, we need a prior on the distribution of these transition times indexed by covariates. And so we need it 7 times. And for each of them, guess what our prior probability model will be? For each of them, our prior probability model will be, we assume a DDP, and actually to make life easy, we just used an ANOVA DDP. So for each of these 7 transition times, we use an ANOVA DDP, pretty much exactly what we had in the previous slide. We can fit those 7 ANOVA DDPs to the data. Then we have a very flexible model to learn about these transition times. And that's a very flexible model in the sense, I think I mentioned that last time, BMP, you can sloppily say BMP is always right, in the sense, no matter what the true distribution is of the transition times, our ANOVA DDP prior always puts some probability mass in some neighborhood of the truth, so we can learn about it. It has full support. So we are going to assume ANOVA DDP priors for these 7 transition times. And I think here, here's the same thing, just more formally stated. See T sub k, these are these 7 transition times in the initial flow chart. There's one minor problem. We'll use our ANOVA DDP with a Gaussian kernel, so that it has support on the full real line, whereas event times like transition times, they obviously have to be non-negative. So we just use a log transformation. So we actually model the log transition times. And f sub k, we had the notation already on the title slide, on the previous slide. F sub k is the unknown distribution of the kth transition time. And so what we need is, we need a prior on the f super k sub x, means we need a prior for the transition time k for a patient with covariate combination x. And we use a DDP, and actually it's an ANOVA DDP. It's the one that we had on the previous slide. And we really have 7 instances of these models. There's 7 of these transition times. The likelihood is simply the sampling model for the actually observed transition times. Where like for a real patient, you don't always observe all 7 transition times, right? Can I flip back to the flow chart? I'll just go back to the flow chart. An actual patient, like if you follow an actual patient, obviously an actual patient just goes through one of these trajectories, right? You cannot have tumor response and at the same time resistance. So when we evaluate the likelihood for each patient, we simply evaluate the model for the actually recorded transition times on the basis of that likelihood and our ANOVA DDP for the 7 transition times. We get a posterior, and when all the smoke clears, in the end, we get a beautiful survival regression. So here you see a survival regression for these four different combinations. Those are I think these are 4 choices for entire treatment policies. So this includes the choice of the initial frontline therapy, as well as the choice for the salvage therapies later. And the picture shows again survival functions, means just 1 minus CDF. So these simply, in our notation, these are simply the posterior expectations of, we denoted with F super K. With F super K, we denoted event time for the K-th transition. I did not introduce a notation for the overall time. Are you with me that when I have distributions for the 7 transition times, then that implies a model for the for the overall time, for the time to overall survival. But actually, as I'm speaking here, I notice this is only for one of the transition times. This is the transition time from, I think, progressive disease to death. It was one of the last transitions. So this one is then F sub, was this something like, I think, the 6th transition time in the original flow chart. Then this would simply be the F super 6 sub X. And I just report a point estimate. So let's call it F bar super 6 sub X, which is the expected value of the distribution of the transition time number 6 in the flow chart for a patient with covariate X. Given all the data, we report the posterior expectation. So that allows us inference on these 7 transition times. And then putting together the 7 transition times for any given patient, you can get inference on overall survival. So hidden down here is overall survival. Overall survival is simply the sum of the relevant transition times. And you can see here in the vertical axis, we plot different policies. So these are all different policies. And for different policies, I think it's always a triple. There's like the frontline therapy, first salvage therapy, and second salvage therapy. Frontline therapy, first salvage, second salvage. For all possible combinations of frontline and the 2 salvage therapies, we get posterior predicted overall survival. And well, if you are a patient in that study, which combination would you ask for? I would probably ask for this one, right? Because, oops, it's running away. Right here is, I think, the overall winner. This is the one that does the best. It's overall survival. So assuming you want to maximize that, this would be the treatment that looks the most favorable. So this identifies then the treatment strategy that would be the most favorable. What we did here, like footnote for those of you who care about adjusting for lack of randomization and causal inference, what we really did here was we used BMP to evaluate potential outcomes, to evaluate prediction under alternative treatment assignments of potential outcomes, and trusting that our model is flexible enough to fit any scenario. We can then use simply the potential outcome that looks the most favorable, that defines the optimal treatment. And I can't resist to show you this comparison. This is a little simulation study, and the simulation study in the left figure. So this is just a simulation study to show the use of BNP to adjust for lack of randomization. It's a simulation study where we had biased randomization, and the left panel is a simple simulation study. We just had treatment, there was like treatment or control, and there was a simulation truth for the treatment effect. The simulation truth for the treatment effect is that vertical line. So this is the simulation truth of the treatment effect. And if you ignore the biased treatment assignment and just use a linear regression to evaluate the treatment effect, then over 1,000 repetitions, over 1,000 hypothetical repetitions of the same experiment. This shows the distribution of estimated treatment effect. It's the estimated treatment effect, but not only one, because we're doing a simulation study, so we can simulate repeatedly. So this was like, I think, over 1,000 repeat simulations. In each simulation, we get an estimated treatment effect, and the curve just shows the histogram of the estimated treatment effects over the 1,000 repetitions. So if you totally ignore the biased treatment assignment, you get it totally wrong. Yeah, you estimate it somewhere around 4.5, and the truth is 2.5. Many of you might know inverse probability weighting. If you use inverse probability weighting, that's that blue curve. This is inverse probability weighting of treatment assignment. You correctly adjust for the biased treatment assignment, but with quite some variability. There is then another one that's known as double robust method or augmented inverse probability weighting. That's this one here. And again, you correctly adjust for the biased treatment assignment, but still some variability. And the red one shows exactly the same using the BMP model. So you're correct. Oh, the BMP model, in the end, there's a little bit of a bias. It's not perfectly centered at the true treatment effect. There's a little bit of a bias simply because we introduced prior bias, but it still compares quite favorable. And I don't want to spend too much time on the right side. That's a summary of another simulation study. In that simulation study, the simulation truth did not match the analysis model. And in that case, double robust methods. So this one, the green one is again the double robust method, and the blue one is inverse probability weighting. Since the analysis model did not match the simulation truth, no surprise, it's totally off. Yeah. This was just a quick commercial for using BMP for adjusting for lack of randomization. I have another little example coming up, and then some variations. I'm thinking for a moment, should we skip the next example? I'll just go fast on that example. It's just another example again, using the same probability with the same BMP prior for dependent event times. In this case, it's an application to what is known as semi-competing risks. There is, so for these are patients, these are brain tumor patients, and we observe progression and survival for each patient. And it's semi-competing risks, because after progression, you can die, but after dying, you cannot show progression anymore. So you have to do you have to be careful in your inference there. You don't want to recommend a treatment for better progression times, and the progression times only look better because all the patients die, right? So you want to adjust for that. In that example, we have now bivariate event times. Patients have there's this pair of progression time and survival time under two treatments, 0 and 1. So we have two pairs of two bivariate event times, and appropriate summaries of that is what you report to compare treatments. And again, we use ANOVA TDP as a prior for these pairs of event times. Maybe that's all I should tell you about this for the moment. And let's jump over the pictures there. And I want to still move on to at least one other model for families of random distributions. Maybe also a good question to pause for a second. Are there any comments, questions about maybe about the previous example still, which we talked about at length, longer than what I had actually planned? I hope I didn't overdo it with the examples. Like I just wanted to demonstrate that you can actually use these BMP models in reasonably complicated applications and get useful results, which is not always true for many super fancy models. Yeah.
Peter, what about the description of uncertainties of these curves that you're showing?
Oh, good question. The question is about see here in the left panel, I showed you the inference. I showed you the posterior inference for one of these transition times, and I showed you like the estimated distributions for there's like 4 different covariate combinations. And by the way, I did a mistake. These are not treatment policies. These are just treatments because we're just talking about one of the transition times. And so Alex comments that I only show a point estimate of the unknown distribution, but actually the model actually gives you a full posterior distribution on these. So the model gives you not only a point estimate for the f sub x super 6, which is the transition time from progression to death. The posterior inference would actually give you a full posterior distribution on this guy. It would have become messy to still plot it in the same picture, but by hand I can easily add it. Let's add it here by hand. I don't know how to plot a distribution on distributions. The best thing that always comes to my mind is spaghetti plots. Yeah. So the red line shows the posterior mean for a particular x, and then in faint gray, I could take like posterior draws and add them here. So I would add like some posterior draws here, and maybe add like 10 different spaghetti. So I could add 10 spaghettis to show the uncertainty. I didn't want to do it on this plot, of course, because adding 10 spaghetti to each of the 4 colors would become a really busy picture. But it's a good point, because that's actually the strength of the BMP approach, that we get a full posterior distribution on the unknown distribution. Do you realize that we are talking about distributions on distributions? Like our random quantity, our unknown parameter is a distribution. So in the end, we have distributions on distributions. You see the little bit. Here in the right picture. So this is now the each of them show the. Oh no, it's just a sum, like it's the expected overall survival. But the uncertainty that is shown in the box plot is actually uncertainty that arises from the different spaghetti in the left picture. I see there's another question here.
Yeah.
So the ANOVA DDP is the prior for the distribution of y given x. Yes. Why do you say and mx? Like the ANOVA DDP is the prior for the family of distributions of y indexed by x. Oh, and the construction of the ANOVA DDP could be, for example, to put a Gaussian process prior on the mx indexed by x. The ANOVA DDP does not use a Gaussian process. The ANOVA DDP, you simply use a multivariate normal for the ANOVA effects. So for an ANOVA, all what you need is a finite number of ANOVA effects. Does that kind of address it, Ching Ching? So it's can be a little bit confusing, because the DDP is a distribution on distributions, right? But once you get used to that, distribution is just a random element like many others, right? And once you get used to that, you can also talk about distributions on distributions on distributions, which we shall do tomorrow in the end, hopefully still. Like the NDP, the nested Dirichlet process, or the HDP, those are distributions on distributions on distributions, and you can keep on going forever, of course. That's how people can build entire careers on it. So the next example I thought was getting too much detail. Let's move to another approach of doing this, which I always thought was very clever, because it's very easy. Huh? So again, like it's not the DDP, it's going to be a different one. But the problem is the same. We are concerned with, we want to construct a prior probability model for a family of random distributions. We want to specify a prior for a script G here. Could be, for example, the family of overall survival distributions for patients indexed by covariate vector X. Here's the trick. Maybe it's easiest to show in a picture. Let's draw this one, like slightly different arrangement of the picture. See, here is X1 and X2. And for each, like what we want now is G is the family of random probability measures indexed by, well, any pair X1, X2, right? So for any pair here, we want to have a prior for a random probability measure. So each of these points here indicates G sub X. I can't draw the G sub X because it would be a third dimension going out of the screen now, yeah? But I can highlight the whole idea because the idea is very simple and therefore ingenious, yeah? What they simply do is they specify a few, see, I think of those as like typical patients. So think of a few typical patients, like there is like an old white man, young white man, blah, blah, blah. So you might think about a few, you might think of a few typical patients, maybe like those 6 specific choices. Let's call this one G1 star, G2 star, G3 star, and so on, at specific covariate values. So this is the typical patient at covariate value X1 star. I think it was my young white male, X2 star, and so on. Then what we do when we see someone, like when we see a patient who falls somewhere in between here, sorry, let me back up. We're only going to put the prior probability model on the red. So we're starting with the prior probability model on the red guys. Actually, here's the prior probability model on the red guys. We simply assume independent Dirichlet process priors for these. Think of they're like knots in a, they're really like the knots in a spline almost, yeah. Like we put the prior probability model on the red guys, on those reference covariate values, and then we define a random probability measure G sub X for any of the X's will simply be, this will simply be a weighted average. We'll simply use a weighted average of, like to construct the G sub X, the blue G sub X there, just use a weighted average of essentially the neighboring reference red G sub X star. That's the whole idea. So the idea is, instead of specifying a prior probability model for all the infinitely many blue GX, just specify one for a few selected red GX star. If they are separate enough, you can even assume they're independent, the red ones. And then the blue ones are just weighted averages of those. That's it. So that just spells out the slide what I had on in the picture on the right side. We start with independent prior probability model on the red references G star sub J at reference locations XJ star, and then if we need G sub X for any arbitrary X, like the blue GX over here, for example, of the blue GX over here, for example. Then we just take a weighted average where the weights can be based on some kind of relative distances. That's it, ingenious, simple, and easy. Footnote, the first author here, many of you might know him, David Dunson. So David Dunson, a lot of his early career was built on DDPs, to the point that some people think that the acronym DDP stands for David Dunson process. It does not, yeah. But he has done it. He has contributed a lot in that literature, so it would not be unreasonable. So that's all I wanted to tell you about there. We did, they call it WMDP, the weighted mixture of Dirichlet process. Yet another one. So do you get the drift here? The common theme is this. The common theme is we want to have a prior probability model for a family of probability measures indexed by covariates. That's the common theme, because that's how I think about regression. Yeah, like remember our first slide today. We think of regression as just probability models for families of distributions indexed by X. So we had now two of them. We had the DDP and we had the weighted mixture of Dirichlet processes. Here's one more, which is almost my favorite for a variety of reasons. So nobody screamed, but there's something you could have complained. In the entire construction, like in regression in general, I always implicitly assume, did you know all the covariates? Like for this entire construction in the last few slides, for that to make sense, for every patient, you have to know all the covariates. Now, depending what the covariates are, some of the covariates you might just not have for some of the patients. They might be meaningless. For example, if this could be some, one of the covariates could be parity, like number of children, meaningless for men. If you have some cancer, that's for men and women. Some covariates might just not be recorded, like they might be biomarkers, some protein expressions, and they might just not be recorded. So in many applications, you run into situations where you don't have complete covariates for everyone. And for such situations, one of my favorite approaches is the next one, to talk about the regression by partitions. And I want to talk a little bit about that. We'll only talk very little about it, because we'll still talk about partitions on Wednesday. Oh, so really very little about it. Here's one way to talk about, one way to introduce a regression. If we first introduce a partition of our experimental units, can we just call the experimental units patients without loss of generality? So we first introduce a partition of our patients into subpopulations. If that partition is indexed with covariates, then that means we are placing patients into clusters based on their covariates. And for each covariate, for each cluster, we have then a cluster-specific sampling model, a cluster-specific mean survival distribution. Both of them together define a regression. Let's see whether I can draw a little picture to that. There's so much space on that slide, I can even do it here. I'll try a three-dimensional picture, which is always dangerous. So here's x1 and x2. I need 3 dimensions because I want to talk about regression. So eventually there will be here like the 3rd dimension, let's call it generically y, might be overall survival or whatever is the outcome of interest. And I just want to draw a picture to the story on the left side of that slide. I promised you we would start with a random partition of our patients indexed by covariates. That means if these are the patients, so the blue points here in the blue plane are the patients, we want to do now a random partition of patients indexed by covariates, which means that patients with similar covariate values will favor them to end up in the same cluster. If you have 2 patients who have the same prior treatment history, they're more likely to be in the same cluster than 2 patients who have very different prior treatment history. So on the basis of that, we might then create clusters here. Say we might have here the yellow cluster. We might have here the orange cluster. And we might have here the purple cluster. There's now 3 clusters there are 3 clusters indexed by covariance. Let's give names to the clusters. This here is CAP C1, CAP C2, the orange one, and CAP C3, the purple one. And for each cluster, we might now have a cluster-specific sampling model. Might be as simple as just a mean outcome. If the Y is overall survival, there might not be, let's make it like this. There's a cluster-specific mean overall survival. Let's call it mu sub 1. Patients in the orange cluster say they have a better prognosis. They get a, they have a higher overall survival. So this is mu 2. And the purple ones say if you're in the purple cluster, it's really bad news. Then here's mu 3. Can you see how this defines now in the end implicitly a regression? Because depending on your covariates, if the covariates are there in the left lower corner, you're most likely yellow. If the covariates are in the right upper corner, you're most likely orange. If the covariates are in the right lower corner, you're most likely purple. And that way, can you see that for a new patient, if we consider now a new patient, here's a new patient coming in. That new patient is yellow with probability 70%, orange with probability 20%, and purple with probability 10%. Can you see that that way we are getting then like an entire response surface, something like that? So this here can then become the expected value of Y for the next patient, given the covariates for the next patient, integrating over everything else. Like conditional on conditional on clustering that patient, the patient is either yellow, orange, or purple, and gets either average, high, or low mean survival. But by the time we average it out, we get a nice response surface. I will talk about it still tomorrow, coming up, because I want to first talk more about probability models for the clustering. I want to talk about probability models to create this yellow, purple, and orange cluster. And today, I still want to talk more about another aspect of BMP regression. It's really another use of BMP regression. It's a very simple one. Don't expect anything complicated coming up. It's so simple, it's almost embarrassing, but it's very useful. Two-line executive summary. We can, once we have a BMP regression, once we have a probability model for BMP regression, we can very easily use it for classification, for non-parametric classification, and with the following little trick, and it's nothing difficult. If we have, so if we have the following situation, if we have a categorical xi, for simplicity, let's assume it's just binary, so it's just say 0, 1. In our application, it will be normal pregnancy and abnormal pregnancy. So there's a categorical covariate. And say our inference aim is to classify a new patient as either, well, x equals 0 or 1. In the application, that will be for a future woman. We want to make a prediction, normal or abnormal pregnancy. And then we have some data. Say the data yi conditional on a patient in xi equal 1 comes, so if it's conditional on xi equal 1, it comes from f1. And so there's a distribution of responses under x equal 1. There's a distribution of responses under x equals 0. Or in general, there's a family of distributions f sub x for x across all possible values. If we go non-parametric Bayes on that, what we need to complete the model, we need a prior. Here's a prior for that family of random probability measures, f sub x. For example, we could use the ANOVA DDP. And at this moment, we just have a, like at this moment, if we stop here, we just have a probability model that would allow us to fit the data. we cannot yet answer the question of interest of classifying a new patient, because that model that I just spelled out assumes the X is given, like we are really conditioning on the X. But it's trivial to augment that model, do a joint model on X and Y, simply add a prior on the X. Since we assume that the X is just binary, this is as simple as it gets, yeah? All we do need is a probability of X equal 1. So we augment the model to a joint model on X and Y by introducing a model for X equal 1. Yeah, that's it. At this moment, you see that these two lines together, we have now a probability model for the pair XY, and it's indexed with the, like let's note with script F, that pair of distributions, and pi is another parameter, right? On the basis of the observed data, like the recorded women, we can get a posterior distribution on script F and pi, and then we get posterior predictive inference for a future patient. In particular, we can get the probability of xn plus 1 equal 1 given yn plus 1, and well, given all the other data, we get a posterior predictive inference for the future patient being, well, in this case, that would be abnormal pregnancy. And that's exactly what we did in the following little example. So that's it, yeah? So really the only addition to what we had before was this trivial line. That's it, nothing else. Like everything else was just vanilla DDP, like straightforward DDP for a simple covariance space. It was just X equals 0, 1. Here's the example. Maybe let's start with the sampling model, because there's a little twist to it. The twist is we actually put the DDP not on the outcome itself, we put the DDP on the random effect, but that doesn't change anything deep in terms of this model structure. So here's our sampling model. The data are some hormone measurements over time. So you can see the, in the picture, you see the data. The black lines are for women who are going through normal pregnancies. This is data from somewhere in Chile. And there's some obvious trends. The dashed red lines, those are abnormal pregnancies. So when you stare at that, like with a single measurement, you can't tell anything, right? But as you get as you get longitudinal repeat measurements for a woman, evidence builds up, and you can eventually probably tell whether it's a red one or a black one. That's what this is all about. So here's our sampling model for YIJ. So these are the YIJ, where I index is the patients and J index is the repeat visits. YIJ is the hormone level for patient I on repeat visit J. XI is an indicator for normal versus abnormal pregnancy. And here's our model. We just assume, can you see this here? This is just parameterizing like this typical shape, yeah? It's like, these functions probably have a name. Are these like the Emacs functions or something? I think these are commonly used in pharmacokinetics or something. In the end, it's just a simple function parameterized with there are two fixed effects, beta 1 and beta 2. Tij is just the time of the visit that is given, and there's a random effect. So the theta I is a patient-specific random effect. And we are now using the DDP, we are now using the ANOVA DDP on the random effect. So not on the Y itself, but we use it on the random effect. Didn't even write it here. So we're using an ANOVA DDP prior on the random effect. So come on, no. So it should have come, like this is the sampling model. I have to complete it with a prior. Like remember our first half an hour review of Bayesian inference. When you have a sampling model, like the sampling model defines the likelihood, right? When you have a sampling model, you still need to complete it to a joint model on data and parameters by adding a prior. The prior, well, I need a prior on the fixed effects. I think it was just normal priors, yeah. Those are easy, nothing special. And I need a prior on the random effects distribution. Sorry, I should have still added here. There is the random effect. We assume that the theta I given xi equal x comes from f sub x. And then we have a prior on f null and f1. And that is where we use the ANOVA DDP. So we use an ANOVA DDP on the random effects distribution. Here is what this becomes in the end. You see in the left picture, in the left figure, you see inference on the f null and f1. Oh, this is addressing what Alex asked before, right? See here you see the, so in black is the f null. So the dashed line is the f null bar. And the many spaghettis, they show draws from the posterior. F null from P of F null given the data. And similar in red, that shows the F1. And again, the dashed line shows the posterior mean. And all the spaghetti show the posterior uncertainty. And once you implement inference in this model, we can also do classification. In the right panel now you see what would happen with a new patient. Let's first focus on the black patient. So patient number 13 here. The woman comes in, and at the first visit you observe like some hormone measurement. And what we plot here on the vertical axis, this is the probability of xn plus 1 equal 1, the probability of an abnormal pregnancy for that woman, given her data yn plus 1, and this is like longitudinal measurements, so yn plus 1 g. And we plot it for like for the first observation, I think 0 means before we get to see anything, yeah? 1 is after seeing the first observation, second observation, and so on. Before we see anything, our chances are 50-50. And then it actually splits very quickly. That was actually, so very quickly we get convinced that that black woman most likely is a normal pregnancy. Like the probability of xn plus 1 equal 1 goes very quickly to 0. And then the red woman, initially also the same probability of abnormal pregnancy. Very quickly we get convinced its probability of xn plus 1 equal 1 is close to 1. That's all I wanted to tell you for the moment about BMP regression. Was of course a little rushed and a little selective, but I hope giving you the flavor that it is not all that difficult to put super flexible priors on general regressions without assuming specific parametric models. In many applications, that's simply not needed, but in some applications, you actually need that additional generality, and it can really help you address problems. I want to show you one more picture. It's not specific to regression, but just summarizing a little bit what we did so far. It's just like there's a proliferation of acronyms, right? So just wanted to put them all together once. See, here's the Dirichlet process, the first thing we ever had. Today we talked about the DDP, and we could have added here the ANOVA DDP is just a special case of the DDP. Yesterday we had already the polio tree. We had normalized random measures. I just introduced them as normalized random measures. What else did we have? Oh, we did have the polio urn. We talked about the stick breaking construction. Remember, the stick breaking construction was to break these to have these better distributed fractions of the probability mass of size 1. And for the Dirichlet process, we use the beta distribution 1m. In general, you can use a beta distribution AB, then you get more generalistic breaking priors. And the special case of those is the Mueller process. We didn't talk about it. Maybe still today, but for sure tomorrow, we'll talk about product partition model. It's another probability model for random partitions. And we'll talk about we'll probably talk tomorrow about the Indian buffet process. And there are many more, yeah. But the main reason to show you that picture is the arrows simply show how one model is a special case of the other. And can you see how the Dirichlet process drops out as a special case of just about everything? So the Dirichlet process is the most beautiful of all. We run into it everywhere. So this is all I wanted to tell you about nonparametric Bayes regression. And we might still have like some 20 minutes time to start part 3. So we'll start talking about random partitions, but this is a good time to ask things about regression or anything else that might come up. Are there any questions out there?
I do, Peter. How do you decide, for example, in this example that you have just showed us, how do you decide between a parametric model for the likelihood and the non-parametric model for the random effect?
Good question. Honestly, I don't have a good answer. A cheap answer. There's some, like when you stare at these hormone measurements and you stare at the data on the right side, there's an obvious pattern to them, right? They rise and then they level off. So that Emax, that function that we used there on the left side is simply a good way to capture that. And then there are random effects. There are patient-specific random effects. Now I have no clue about the patient-specific random effects. That's why we go non-parametric on the random effects distribution and parametric on the profile here. So cheap answer. I can dream up a parametric model for curves like that, right? If you don't use the one that we have here, you might come up with another one. But I find it difficult to dream up a probability measure of how different patients should have slightly different parameters. It's not a totally clean answer, yeah. There's no, I mean, honest answer or a generic answer would be you try to go non-parametric kind of where it matters, where you don't have like a good idea of what parametric assumptions to make, or vice versa. When you don't have enough data to really learn much, you might have to go parametric. But when you have a lot of data, like for the random effects, I have 170 observations. That might be enough data to learn about a non-parametric function, to learn about something very flexible. Whereas for the profile, for each woman, I think you only have like 4 or 5 observations over time. You don't have that much data. Very cheap answer, but good question, yeah, fair question. So if there are no other comments or complaints or insights, then let's move to the, that's now part 3. And so if you downloaded the slides, you would have this part 3. And we'll not finish that today, but we can start it to part 4 tomorrow still. Yet another, like I tried to organize it a little bit along different types of data analysis. We talked about density estimation. Now we talked about regression. Next one, let's talk about clustering. Clustering is simply about subsets that are non-overlapping and exhaustive. In general, when you talk in general about random subsets without the requirement to a formal partition, then it's known as feature allocation. So by way of explaining the title here, this is simply random subsets that could be overlapping. Whereas clustering that is a synonym for partition, means subsets that are non-overlapping. You often run into issues of random subsets. For example, when you're trying to find subsets of genes that correspond to different biologic functions, there are many genes that are linked with multiple biologic functions. So then you want to look for subsets that might allow for overlap. On the left side, you see one, so here's one typical application. There's on the vertical axis different mutations. And the horizontal axis are different subclones. This is about the fact that you all know the story of how tumor arises. Like cancer, initially you have your normal cells, and at least in a simplified explanation or by high school biology, all your cells have exactly the same DNA, right? And then each time you go through the airport, each time you go through the microwave at the airport, or as you go through life, you pick up mutations. And so some subpopulations of your cells might pick up some mutation, some subset of them pick up yet another mutation, until they pick up too many mutations, and some of them are malignant, and that might develop a cancer. But so the story is that in the end, there might be different cell subpopulations. That are characterized by different subsets of mutations. In this cartoon picture, there's like one cell subpopulation. Cell subpopulations also referred to as subclones. There's one subpopulation that's characterized by all these mutations, like these guys have all these mutations. The second cell subpopulation is this one. They have most of these, and then they have like some additional ones. And the third cell subpopulation, they have that set of mutations and that one. It's important to know that because so if different tumors might have different cell subpopulations, they might react to different treatments. Like if you have a treatment that targets particular mutations, that might or might not work for different subpopulations. But back to the statistics, when we try to learn about such subclones and subpopulations, then we need a probability model for subsets of mutations. So we could have a probability model for a particular subset of mutations. And that will be exactly one of the models that we shall talk about. Yeah. On the right-hand side is a different story. Like favorite ball game of people in bioinformatics, and I bet you have seen your share of related talks. Clustering of proteins, clustering of genes, clustering of proteins, clustering of patients, always with the idea in the back of their mind that, so to start with, see in the horizontal axis are proteins. To start with, we're just clustering proteins. So here is like one cluster of proteins. Let's call it W equal 1. Here's the second cluster of proteins. Just focus on the horizontal axis for a moment, yeah? And so on. Then building clusters of proteins is with the idea that different clusters of proteins might correspond to different biologic functions, so they kind of act together. And then for each cluster of proteins, so nested within a protein cluster, we are clustering patients. So on the vertical axis are patients. So with respect to the first biologic functions, the patients might cluster like this. However, with respect to the second biologic function, patients might cluster entirely differently. Difficult to draw on top of that picture. And so on. So that's a very simple notion. Like when you cluster people, like Alex and me, I think we cluster together with respect to our preferences in statistics. So with respect to our preferences in statistics, Alex Schmidt and me are in the same cluster. Now I have no clue about her music preferences, but chances are we might be in totally different clusters. Or in other words, with respect to some function, two patients might be in the same cluster. With respect to another function, they might be in different clusters. Or in other words, you might be interested in nested partitions. There is a partition of proteins, and nested within each subset of proteins is a potentially different partition of patients. We'll talk about models like this. So that's what's coming up. To start with, we'll just talk about probability models for clustering. Any questions, complaints? You should complain about one thing now. We promised you lectures on nonparametric Bayes, and one of the first things we did on Monday was we defined nonparametric Bayes as probability models on infinite dimensions, like probability models for infinite dimensional parameters, like an unknown distribution is an infinite dimensional thing, right? A partition, there's awfully many partitions of patients, but only finitely many. Like if you give me 173 patients, there's a finite number of cluster arrangements that I can build. It's awfully many, but it's finitely many. So you could say, strictly speaking, that's not nonparametric Bayes. And I would agree with that. But you already know too much. Remember from yesterday, when we introduced the Dirichlet process mixtures, we already talked about how a Dirichlet process mixture implicitly induces a probability model on a partition. So for that reason, random partitions and random subsets are usually considered nonparametric Bayes. So that's it. Let's start talking about that. So plan for today. Sorry, plan for this part, which we are not going to finish today. Yeah? We'll talk about clustering. I think we can start with that. And then tomorrow we'll talk about nested partitions. That was the slide. There was the picture on the title slide. We'll talk about random subsets, and then we might talk about one of my pet themes, dependent partitions. But let's start talking about clustering. And the first 2 or 3 slides, actually just repeat. It's exactly what we had before. Just to remind you of where this comes from. So remember when we talked about Dirichlet process mixtures, we started with a random probability measure, excuse me, we started with a random probability measure F, like that F might be generated by a Dirichlet process. We said a Dirichlet process random measure is discrete, so you can actually explicitly write it as a sum of point masses like this. If you want to make the discrete random probability measure, if you want to make it into something continuous, remember our trick was, to replace these discrete point masses, replace them by little Gaussian kernels, or same thing, in other words, do a convolution of the discrete probability measure with a Gaussian kernel. Then what we get in the end, we simply get a Dirichlet process mixture of normals. We had it yesterday. And then remember we still said when you try to think about this mixture of normals, a natural thing to do is to replace this line. Let's give it a number. Let's call this line 1. I think it was line 1 on the slides yesterday. You can replace line 1. This is totally equivalent to these 2 lines together. We can introduce a latent red variable theta I, and we say yi given theta I comes from that kernel, in our case a normal, and the theta I comes from the F. That's exactly equivalent to line 1 up there, because when you marginalize, when you multiply the 2 and marginalize out the red theta I, you're exactly back to line 1 up there. So this is just by way of reminder where this came from. The important one is, remember that we said there was this funny thing that I already highlighted yesterday, was more than just a casual footnote. there's this funny thing that theta i's are a sample from a discrete probability measure, that f here is discrete. They are sampled from a discrete probability measure, so there will be many ties. Let's denote with theta sub k star the unique values. There's typically a small number of unique ones. So say if if we have n equal 173 patients, the k might be as small as just 6. It's actually asymptotically, it's something like cap m log n, where m is the total mass parameter. So actually asymptotically, it's something like, cap m times logarithm of n, where m is the total mass parameter in the Dirichlet process prior. Remember, the G.E.P came with two hyperparameters. We need the total mass, the m, and the base measure. And remember, we also said, instead of giving you the theta i's, so I can either give you the theta i's, or totally equivalently, I can give you the sets and the theta stars. That's the same. The set a cluster membership indicator. If I tell you that the ith theta is tied to the jth unique value, and they give you the unique values, I have told you all the thetas, right? And I told you already yesterday that something special about the Dirichlet process is that we can actually spell out the joint distribution of the theta i's. So you can actually spell out the joint distribution of the theta i's, marginalizing the f. When you come to think of it, it's actually a very important thing for implementation, because the f is the unknown distribution. It's infinite dimensional, whereas the theta, that is only of size n, because there is one theta, one latent theta I for each observation, right? So the theta is finite, so I can represent it in my computer. The f is infinite dimensional. I cannot represent it in my computer. So it's actually important that we can talk about this in closed form. Already yesterday, we said we are going to represent the marginal distribution of the thetas. Instead of talking about the thetas, remember I told you totally equivalent. Instead of the thetas, I can tell you about the theta stars and the set. It turns out the prior on the theta stars is as simple as it gets. The prior on the theta stars is just IID from the base measure. I mean, this is correct, but I can actually see that more specifically. Can you still flip back to the previous slide, please? I'll slip back to the previous slide. The F comes from a Dirichlet process. F comes from a Dirichlet process with M and base measure F star. Then we know that the theta stars sub G, those are IID samples from the F star. So can write this as. So I don't need to use a generic P here. I actually know what it is. It's the base measure F star. That is simply because, remember the stick breaking construction, the unique values, those are simply some specific atoms, and those atoms were generated as IID from the base measure. That was part of the stick breaking construction. And important, and that's what we should talk more about, importantly, the joint distribution of the cluster membership indicators, that's easy to characterize. That's actually the polyurn. And I think we already had that statement on the slide yesterday. And I'll just slightly modify that statement. The way how I wrote the joint distribution of the cluster membership indicators on the top line of the slide now. The joint distribution of the cluster membership indicators, we just wrote it as a product of increasing conditioners. And each of these conditioners is easy to write. Down here you see the probability of the next patient being in cluster J, given all the previous patients. The next patient goes in cluster J with a probability proportional to Nj. And the next patient doesn't go into any of the current clusters, but has a new unique value with a probability proportional to m. We are reminded the nj is just the size of the G.E.P cluster. So nj is the number of theta i's that are tied to the G.E.P unique value theta j star. There is one more thing I should tell you. Here I told you that only as the conditional distribution of the next one given the previous ones. I claim that exactly the same format is true for any one of them given the others. Can I write boldface set sub minus I just for all the other sets minus the ith one? So this is set 1 through I minus 1, not the ith one, I plus 1 down to n. It turns out the conditional of the ith one given all the others has exactly the same form. It is, let's just write it as proportional. It's proportional to, let's call it nj minus and m, where nj minus is simply the size of the G.E.P cluster without the ith guy. So this is the size of the G.E.P cluster without the ith guy. Can you read my notation in the bottom line of the slide now? In plain English, this is just after you take out the ith guy, like we're talking here about resampling the ith guy. Talking about resampling the ith guy, when you take the ith guy out of the G.E.P cluster, which for many clusters is not going to change anything, then nj minus is simply the size of that cluster after you remove the ith guy. Claim that formula that was valid for the m plus first guy, exactly the same formula is valid in blue for the ith guy. The reason why that's the case, like you don't have to show anything. The reason why this is obviously the case is because the entire, like we came here from a construction that was totally symmetric in the in I. Can you flip back to, I think I have to go like a few slides back. Actually, this is enough. If I go back here, those first two lines, they defined my model, right? Do you see that these first two lines are totally symmetric in I? Like you can do any permutation of the patient indices and you get exactly the same probability model. Or in short, we can say it's exchangeable in I. It's exchangeable in the patients. So since our model is totally symmetric with respect to the I, whatever is true for the n plus first one has to also be true for the ith one, because we could arbitrarily, we could simply, I should have made it even simpler. I should have said the thing is true in blue because we could relabel our patients such that patient I becomes patient n plus 1, saying the same thing. This blue expression is actually important because we need it for posterior simulation. Remember, in our first 30 minutes, we talked about the G.E.P sampler and MCMC, for which you need complete conditional posterior distributions. This is the complete conditional prior in blue. If you multiply with the likelihood, you get the complete conditional posterior, and that we can use for posterior simulation. So it's actually important for that. And I still have a few minutes. I could either quickly talk you through that example, or are there any questions or complaints, comments? Feel free to ask questions. Like sometimes when things are unclear, it's not easy to ask a pointed question. Yeah, you can just ask to repeat something in different words, and I'll try. It's often easily possible. Or not only questions. Sometimes you might have like a sudden insight, like if you have a sudden epiphany. It might be nice to share that. Yeah, if you suddenly see something, just say that, speak out. See, I just don't want to go through that example anymore. I was hoping somebody would say something.
Hey, Peter.
Yeah, thank you.
So for the clustering, this portion doesn't really need to use the continuous kernels, right?
Good point. Quick answer, no. Oh, so quick answer, no. Longer answer, thank you for asking. Longer answer, I needed an excuse to introduce those latent theta i's. Like, see the first two lines now on the first two lines on the screen. I needed an excuse to introduce those latent theta i's because the ties of those latent theta i's, they define the clustering. And my excuse for introducing the latent theta i's was the convolution with the continuous kernel. But you're right, of course. I could have introduced the theta i's without any excuse. I could have simply introduced them and that's it. So fair answer, you don't strictly need it, but it kind of appears naturally when you had the convolution with the continuous kernel. But there was actually in that question was actually a very deep comment in the sense that you could use the Dirichlet process you could use the implied clustering from the Dirichlet process mixture without using the random distribution. And that is actually very much done, and that's something that I should have said. I'll sneak it in here. So if you just use the random partition implied by the Dirichlet process mixture, just the random partition by itself without the random probability measure has a separate name. It's also known as the Chinese restaurant process. Or also known as the polio-urn, for the reason that's on the bottom of the slide. So when you call it that metaphor of the Chinese restaurant process comes from the following picture, and that's a perfect way to finish this, to finish our discussion today. So exactly the same probability model for the random partition, but now without any reference to random distributions. Here's a Chinese restaurant. It's always drawn with round tables. Big Chinese restaurant. There are some people sitting on this table. This is the table small k equal 1. There's 2 people sitting there and k equal 2. Here's k equal 2. Say there's 4 people sitting here. There's 1 person sitting here. And there's nobody sitting here. New person comes in, new customer comes in. When you walk in the past life, when we had things like indoor dining and such things, when you walk into that restaurant and you look for a table now, so assume this is like a big dim sum restaurant and you walk in there like on Sunday morning, you're in a very social mood. Like you go out for your dim sum on Sunday morning because you want to hang out with your buddies. Which table do you go to? If you join table K with probabilities proportional to the number of people who sit there, and a new table with a probability proportional to cap M, then that's exactly the probability model on the left side of the screen. So if your probability of joining table 4 is proportional to 4, probability of joining table 1 is proportional to 2, etc., then you get exactly the model that we have on the left side. And at this moment, there was no mention of a kernel, no mention of an unknown distribution. So that's I think that was probably below the question. And that was a good one. So this is known as the Chinese restaurant process. I would actually go to table 4 because I get the most food there, but that is just me, yeah. So thank you very much. and hope to still see you tomorrow. Tomorrow we'll talk more about random partitions and then hierarchical priors. Like hierarchical priors will be probability models on probability models on probability models.
Great, thank you, Peter. Thank you so much. This is really nice.
Thank you, and I hope you're hungry now and can go.
Yeah, after this Chinese
you guys on Eastern time.
Yeah, it's time for lunch for you, right?
Yes.
Enjoy your lunch, and
thank you.
See you tomorrow. Thank you so much.
See you tomorrow.
Bye-bye, everyone.
Bye.
Take care.
Bye.